In this video, we're going to examine a problem where we have a mass, an object, pushed with a constant force for a given distance, and we'll try to determine the speed of the object after it moves through that distance. And then in part B, we're going to let the object go up a ramp that has friction and see how far it goes up the ramp. So for the first part, we're moving on a horizontal surface that has no friction. A 65 kilogram object, constant force of 14 newtons, and we're going to move 12 meters. This is a problem where we can apply the kinematic equations. Because the force is constant, the acceleration will be constant. We start at rest with initial velocity of 0. We move the 12 meters, and this part A of the problem stops before we go up the ramp. To do the kinematic equation, force is not in those equations, acceleration is. So we first find the acceleration, 14 newtons divided by 65 kilograms, and 0.2154 meters per second squared. I tend to keep 4 digits at least in my intermediate answers. We'll round off more towards the end of the whole problem. So the kinematic equations, we do not know the time to travel the 12 meters. So I pick one of the kinematic equations that has the final velocity but does not have time. So v squared, the final velocity squared, the initial velocity squared is 0. 2 times the acceleration times the distance traveled. So v squared equals 2.2154, and all that multiplied by 12. You should stop and work this out on your own calculator. And make sure that you're following along the mathematics, but I come up with 2.274 meters per second. That's our velocity, off the speed off to the right as the object is moving. Is there another way to solve this problem other than the kinematic equations? And the answer is yes. We can use the concept that work done on the object is equal to its change in kinetic energy. We have a constant force here and the distance given, so we can use work is force times distance. And we have no change in the potential energy, so all the work is going to kinetic energy. And the kinetic energy 1/2 mv squared. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Again, this is along the 12-meter stretch before we reach the plane. This part A, there's nothing involving the change in potential energy. So we have the work done, 14 times 12. We have the kinetic energy 1/2 times the mass that's known and times v squared. And not too surprising, we get the same result. For our speed, our velocity, the speed 2.274 meters per second, directed off to the right would be our velocity. Now, the second question would be what's the distance it slides up the incline? What's our position on the incline measured along the slant? So you can see in my diagram of the problem, x, the unknown, is along the slant. H is involved, but we'll see how we handle that. So in this problem, there are some forces to consider. We have the force of gravity, mg, straight down, 65 times 9.8. That force is not useful in the problem because it's not directly parallel to the incline, nor is it perpendicular to the incline. So my first step is to find the components of the force of gravity, that one component is parallel to the plane, the other component is perpendicular to the plane. So I've drawn a little triangle here. If you draw this such that mg, the weight, is the hypotenuse of the triangle, the angle at the top of this triangle will be the same as the ramp angle, so 22 degrees at the top. And then one side is perpendicular to the ramp. This will be equal to the normal force. The box is not accelerating away from the plane or into the plane. So in this direction perpendicular to the plane, the net force is 0. The normal force of the plane pushing up away from the plane is equal to the component of the weight pressing into the plane. The component of the weight is 65 times 9.8. That's the hypotenuse, multiplied by the cosine of 22 degrees. That gives us the adjacent side to the angle. 590.6 newtons, that's our normal force. we can also calculate, but not use very much, the component of gravity down the plane. The way I'm going to choose to work this problem is through energy and not the work done by the component of gravity down the plane. That would be another approach, but I'm going to use the energy concept. Well, the force of friction, coefficient times the normal force, 0.13 for the coefficient. We found the normal force, 590.6, so our force of friction is 76.78 newtons. Then, here's our conservation of energy equation, including the work done by the non-conservative force. Our supply of energy, when we just started going up the ramp, the object was in motion. We found that in part A, so 1/2 mv squared here. On the horizontal surface, I'm going to call h equal to 0. The potential energy is mgh, h being a vertical distance, and I'm going to have the reference point h equals 0 be the horizontal surface. So at the bottom of the ramp, we're at the horizontal surface. The potential energy as we start up the ramp is 0. And then the non-conservative work, this will be a negative term. The force of friction is acting opposed to the motion, so it's down the ramp. It's coming back this way. The motion is up the ramp. The force and the distance traveled are 180 degrees apart. When that happens, the work is a negative number. Then our final kinetic energy will be 0. We want to know how far we go up the ramp. When we stop, there will be a potential energy. So we have our initial kinetic energy minus the non-conservative work. 76.78 is the force. X is our unknown distance up the ramp. And then we have mgh. The final energy is in the form of potential, 65 times 9.8 times h. There's a problem in solving this directly because there are two unknowns. X is our distance up the ramp. H is the vertical height of the box now, or the sled, above the horizontal surface. So H and X are not independent. So if we focus over here just a little bit, a triangle with a 22-degree angle, X is the hypotenuse along the incline. H is our side opposite the 22-degree angle. It's vertical. So the sine is equal to opposite divided by hypotenuse, H over X. I can find the value of sine of 22 degrees, multiply both sides by X. And now I have something I can substitute and replace H with something that has the X variable in it. So we do that on this line. And taking the 0.3746 times 65 times 9.8 delivers 238.62 as the coefficient of X. We gather together the like terms. So I have to add 76.78x to both sides. We have 168.06, that's our kinetic energy, equals 315.4 times x. And solving for this, our x is 0.533 meters, and we have a distance up the ramp, 53.3 centimeters. That's how far the sled will slide up the ramp before coming to rest. So I hope you followed along with that. Two ways to come up with our speed at the end of 12 meters. Kinematic equation, or the principle that work is equal to the change in the kinetic energy. And then doing the calculation moving up the incline, I chose to take an energy approach. This could also be done with work of gravity against the component of gravity, the 238.6 newtons times x, and you already saw that number came up here. But I chose to do mgh, the more traditional vertical potential energy, and then substitute for h. So hope you followed along with that. If not, pause the video, go back to where you need to. Make sure you're doing these calculations on your own, and ask your instructor if you do have any questions about the method that's employed here. If you'd like some other physics and astronomy videos, short tutorials, and example problems, these two websites list those videos that I've made. These is a free website. You do not give me your email address. Just look at the list of videos and find out what's useful for you. And appreciate if you would subscribe to my YouTube channel. Hope you keep practicing problems and grow in your knowledge of how to solve physics problems.